Now I want to look at some tests for convergence. That's going to seem a little bit ridiculous. It's going to seem honestly a little bit useless, but it's definitely not useless because when this test for convergence applies, it sticks out like a sore thumb, and it can be very helpful for finding if a series converges or diverges really quickly, right? So let's start by defining our series, right? We have the sum of some series will denote a sub n, right? Starting from n equals some integer k to infinity, right? This is our series, right? Now I want to lay out that weird criteria. Let's say a sub n is equal to -1 to the n power times some other series b sub n, or it's equal to -1 to the n plus 1 power times some series b sub n, right? So if our a sub n fits this kind of structure we've written out, and our b sub n is greater than or equal to 0, we're on our way to using our alternating series test for convergence. That's what we're doing today. So we have these set up so far. Now, if the limit, right, if the limit of our other series b sub n as n approaches infinity is equal to 0, right? We need this to be true. I'm going to put a little star, right? If it's equal to 0 and if b sub n is a decreasing series, right? So I'm just going to write this decreasing, and I'll abbreviate it like that. Then we can for sure say that our series a sub n converges. Now again, this all seems very arbitrary and very wacky, but we're going to do a little example to show where this will help us, right? So let's go look at that example. Okay, so we're going to have the sum, right? We're going to do our sum from n equals, let's say, I don't know, let's just say 3 to infinity, right? And this is what our sum is going to be. We're going to take the sum of -1 to the n plus 1 power over 5 to the n. Now again, this one sticks out to you like a sore thumb, right? Because you're already seeing that -1 to the n plus 1 criteria that we laid out. So we can kind of separate this sum, right? We can say that this is the same thing as the sum from n equals 3 to infinity of -1 to the n plus 1 power times 1 over 5 to the n. And now we meet that criteria from the previous slide here. Let me go back to it real quick. We have this format where we have our -1 to the n plus 1, and then we have some series. Our b sub n in this case is going to be 1 over 5 to the n power. Okay, so now we can start going through some stuff. Clearly, b sub n is greater than or equal to 0, 1 over 5 to the n. Here, let's actually write down that b sub n is going to be equal to that. So b sub n is equal to 1 over 5 to the n. So clearly, this is greater than or equal to 0, right? Now we need to check those two criteria. We need to check that the limit as n approaches infinity equals 0. So let's do that, right? The limit as n approaches infinity of b sub n, right? And clearly, if we plug in, if we go to infinity for n, we have 1 over 5 to the infinite power. Our denominator just dominates the numerator. It's infinite. That's going to be equal to 0, right? So our limit as n equals 0, as n approaches infinity, is equal to 0. So that's great. We've got that. And b sub n is clearly a decreasing series, right? I mean, we can just plug in some n for it, right? Like if we plug in, we're starting at 3. Oh, God, I don't want to write that out. But 1 over 5 to the third, and then 1 over 5 to the fourth, and then 1 over 5 to the fifth. You know, every time n gets larger, our actual fraction gets smaller. So we do have a decreasing series here. So we'll say b sub n is decreasing, right? And we've met all of the criteria we needed. So what was that little point I said last time? Oh yeah, it was a little bit like this. If b sub n is decreasing and the limit equals 0, then a sub n converges. So we can say that our series, here let's get our yellow again. We could say that our series from n equals 3 to infinity of -1 to the n plus 1 over 5 to the n converges. If you made it to the end of this video, thank you for watching. I really appreciate it, and I hope you learned something.